Hi everyone and welcome back to PrepFusion. So today we will be starting with the final and last lecture of electrical machines subject. So this will be the lecture 64 where we will discuss about different types of single phase motors. Okay. In the previous lecture we briefly discussed about the main winding and we did few problems on equivalent circuit numericals. Today we will discuss different types of single phase motor if I change the auxiliary winding. So today I will discuss about the auxiliary winding. Also we will do questions. So this will be the assignment 22 solutions. Also we will do universal motors. So basically if I want to use, what does universal motors mean? Universal means it can work in any supply, can work in any supply. Okay, it can work in any supply. These are what my universal motors are. Okay, so like basically I will make the DC series motor to work as a AC motor, and why it works as a AC motor, that I will explain. Okay, so let's first start the basic concept of auxiliary winding. So auxiliary winding is mostly utilized only during starting. It is not utilized during running condition. So running condition this will be used, and starting condition my auxiliary winding will be used. Okay, this diagram, same diagram I have shown to you at the starting of this lecture, right? At the starting of the previous lecture, if you remember this diagram. So physically this is the actual diagram. Physically that's how they will be placed, but electrical circuit wise, to represent them in circuits, I will do that, I will show that, right? And basically if it is 90-degree perpendicular, only the auxiliary like this is represented to show you that auxiliary winding will be 90-degree perpendicular to the main winding. Okay, so this is the actual diagram, this is the circuit diagram. So here, right, what is the torque developed? So I know both of them will develop a magnetic flux. So mmf, right, mmf, both of them will develop mmf. Let's assume that the auxiliary winding develops a mmf, that is I aux, and the main winding develops a mmf of I main winding, right? So the torque, starting torque developed due to both the auxiliary and the main winding will be interaction, multiplication of IAW into AFMW into the sine of the angle between the two mmf, right? FMW and FAW. Okay, so the thing is, your mmf is proportional to current. mmf is proportional to current, right? So basically it means that my developed torque will be proportional to the main winding current, auxiliary winding current, and the sine of the angle between them. So let's assume that if my voltage is around here, this is my reference, right? And if my auxiliary winding is lagging current, it will be more lagging than the main winding. Main winding will be somewhere here, because it will always run, right? Auxiliary winding will be somewhere here. Okay, and the angle, let's assume that this angle is some theta a w, so this will be sine of theta a w. So your torque will be proportional to this value. Okay, so ultimate aim of our is, now the supply is same, that's why the voltage is same. How can I make it a different phase difference? Basically here I can make it more capacitive or more reactive. Sorry, I made a mistake. Auxiliary winding will be leading. Auxiliary winding will be leading than the main winding. Okay, that was my mistake, because we will use capacitors. So if I use capacitors, what will happen? It will lag less, or sometimes what happens, auxiliary winding can also lead the voltage. If the circuit is purely capacitive, I can use a capacitor of high value, so then the auxiliary winding will lead the voltage because it has capacitance, right? Yes, winding will have its reactance, but this capacitance will be so high that it can compensate that and it will lead. Okay, and your main winding will always lag because your main winding is just a inductance, right? Inductive reactance. So it will always lag the voltage, but auxiliary winding can lead the voltage. Okay, and the angle difference between them will be theta AW. So this is the main purpose. Main purpose is to create a phase difference between the auxiliary winding current and the main winding current, right? So purpose is, what is the aim? Aim is to create a phase difference between auxiliary winding current and main winding current. That is the main purpose over here. So there are many methods, many ways to do it, right? First one is using uh, simple resistors. So I will add a resistance in the auxiliary winding with this is called a centrifugal switch. Centrifugal switch basically means it will turn on during the starting. After that it will automatically be turned off. Okay. So the first one is resistance split starting. Okay, resistance split phase, right? So I will, like, what I will do is I will make the resistance different than this. If I add a resistor over here, this will be less lagging, right? So basically what will happen is, what is the phase difference? So if my voltage angle is here V, what will be the current I in the main winding, right? This theta mw. How will I calculate this theta mw? It's very simple. Theta mw will be equals to tan inverse into xm divided by Rm. Okay, and your theta aw is equals to tan inverse xaw divided by Ra. Okay, and what will happen, this Ra will be much higher. If this Ra is much higher than this Rm, right, what will happen, this theta aw will be much smaller because increase in Ra will reduce this theta aw. So basically theta aw will be somewhere around here. This will be Iaw, this will be theta aw. So that is the basic thing, right? That is what we will do. We will just simply reduce. So what I can say is xa by Ra will be much smaller because this theta aw will be much smaller, the theta mw will be much smaller than xm by Rm. Okay, that is what we will do. That's it. So in resistance split we do this, but of course you remember, if I am adding resistor there is power loss. If I am adding resistor there is power loss. So that is the disadvantage. That is the disadvantage, because if Ra is increasing, right, if I am increasing Ra, if I am increasing Ra, that basically means the I square, Iaw square Ra is increasing, right? So due to that additional power loss will be there, power loss. So during starting this loss we have to bear. That's it. That's the only thing. Okay. Now x by r ratio has to be kept low. So if I want to keep the x by r ratio, what needs to happen? So I want to keep my x by r ratio to be low, right? This x by r ratio to be low. So x should be low, r should be high. So what is x equals to? X, if you remember, it is equals to 2 pi fl, right? So it is proportional to the inductance. So L is, if you remember, it was mu naught n square, mu n square a by L, right? This is what your L was. This we had derived in B6 of magnetic circuit. Okay, so L is equals to mu n square a by L, right? So what I can do is I need to make the reactance smaller, so inductance will be smaller. If this is smaller, so I will make the number of turns less. So this will contain lesser number of turns. So number of turns will be lower. What about resistance? So resistance is equals to rho L by A. Okay. So I want to make the resistance small. So of course I cannot change the resistivity. I can increase the area, so that it can also, sorry, I want to increase the resistance, I have to decrease the area, right? Because I want R to be higher. So either I can reduce the length or increase or reduce the area, both of which will work. Okay. So yeah, in me, what you do, so basically the auxiliary winding, the area is lower, number of turns is higher than the auxiliary winding. Same thing is written over here. So it is a split phase. Split phase basically means I am splitting the phase, right? Phase has been split. So one more important point to understand is, if I am adding resistance to the circuit, and remember both of them together are producing some torque. So 2/3 of the winding is main winding and 1/3 of the winding is auxiliary winding. So both of them together are producing torque, right? So if both of them together are producing torque, so if only main winding was present, then the torque would have been something like this. If you remember at starting, main winding, if only main winding is there, starting what kind of torque we get? So starting, the torque that we get is somewhat like this. Okay, sorry, this is not starting. Okay, this is the torque that we get. Now yeah, now what we'll do, this is the torque due to the main winding, right? Now auxiliary winding is also there at starting. So auxiliary winding will provide an additional torque. So due to auxiliary winding, it will have some starting torque, and it will add, like this will get added with the main winding torque. So this will be somewhat higher, and then after it reaches a certain point, okay, so this torque is auxiliary winding plus the main winding. Okay, after it reaches a certain speed, that is 75%. Generally what we do is, after we reach 75% of the synchronous speed, 0.75 of synchronous speed, so this will be ns here. Okay, what we do, we turn off the centrifugal switch. So there is no current anymore, but still main winding has current, and we know at this speed it will develop some torque. So the torque suddenly reduces and it follows the graph, the main winding graph. Okay, so that is the purpose. Basically we don't want to keep the auxiliary winding always on, because there can be couple losses there, right? So that is the reason why we don't want to keep the auxiliary winding always on. Okay, so this is the torque speed graph for a resistance split phase. Okay, I hope you have understood. So the main winding will have low resistance, high reactance. Auxiliary winding will have high resistance, low reactance. Auxiliary winding is connected in parallel with the main winding during starting. Okay, that is what auxiliary winding is connected in parallel with the main winding during starting. A centrifugal switch keeps the auxiliary winding connected at startup and disconnects it once the motor reaches approximately 70 to 80% of the synchronous speed. Centrifugal switch will be closed at starting, it will be turned off, it will be opened after the motor reaches 70 to 80% of the synchronous speed. Okay, so this is the torque speed characteristics as I was explaining. and auxiliary winding will have fewer turns and smaller cross section area. Reason I have already explained. Okay. So x by r of the auxiliary winding is made lower than that of the main winding to achieve reasonably phase displacement. So I cannot obviously achieve very high phase displacement here because still both of them are lagging, because there is reactance. I am only changing the resistance, right? So both of them are still lagging. So the around the ballpark number, the ballpark phase difference that I am able to achieve is 30%. That is the ballpark phase difference that I am able to achieve. Okay, sorry, not 30%, 30 degrees. Okay, so provides moderate starting torque, because higher the phase angle, higher the torque, right? Because my torque is proportional to sine of angle between theta a main minus theta aw, right? So higher this torque angle, higher this angle, higher this torque. So this is 30, so I will get moderate starting torque. If this is high, the starting torque will be more higher. Okay, so we will see how can I get higher torques. Generally this is used in fans, blowers and washing machines. Okay, so now let's come to the next type of induction motor, that is capacitor start induction motor. Now in capacitor start induction motor, what do we do? We connect a capacitance. That's it. So what will be the phase difference? Now XC will be much larger than XA, right? The inductive reactance. So as it is larger, so basically the phase difference, my voltage is here, my main winding current will be here, that will be lagging. My auxiliary winding current will be here, that will be leading. This will be my auxiliary winding current. Okay, so this is my theta A and this is my theta m, theta main winding, right? So of course now the phase difference will be much larger because now it is leading, this is lagging, so both will be added. Previously here if you see both were subtracted, now the phase difference will be theta am plus theta aw. Okay, theta am plus theta aw, that's it. Okay, so I hope you have understood this point, that is clear. Yeah, so here the phase difference is much larger, so the starting torque will be much larger. Now there are two kinds of capacitor, one is short duty, another one is long duty. So what is short duty? So I will explain over here what is short duty and long duty capacitor. So short duty capacitors are those where I will have a centrifugal switch and where the capacitor will be used only for starting. So short duty ones, as the name suggests, that it will be used only for starting. So used only for starting. And long duty ones, it will always be used, basically used during starting and running. So it will always be used no matter what. Okay, so generally what happens, and the short duty ones are electrolytic capacitor, long duty ones are paper type or oil type. Okay, just theoretical points. So the capacitance of short duty will be higher than capacitance of long duty, because long duty capacitors, if it is always operating, always some current is flowing, so it will not get damaged because the capacitance is lower. Okay, if the capacitance is higher, there are chances of it getting damaged if I use it for a longer duration. Okay, if I use the capacitor for a longer duration, that can get damaged. So why is this useful? So short duty capacitor, their CSD is much higher. So if their capacitance is much higher, then what will happen to the angle, starting torque? So they will produce more amount of starting torque. Actually I am kind of wrong, sorry, their reactance will be much higher. Sorry, they will provide their XSD will be much higher than X long duty. so their capacitance will be much smaller. This will be smaller capacitors than CLD. So if the like, why? Because they will provide higher reactance, so they cannot support higher currents. If the capacitance is very low, they cannot support higher current. Okay, because the capacitance value itself is very low. Because if capacitance value is very low, the voltage rating of the capacitor also will be very low. Voltage rating also will go down, so I cannot always use it. So that's why sometimes long duty capacitors are used. Why are short duty capacitors used? Because the reactance is higher in short duty capacitor. That means what is the auxiliary winding angle? Theta A. What is the theta A? So theta A, if I write, right, theta, what will be theta A? Theta A, if I write down here, it will be tan inverse of XA minus sorry, x, yeah, it will be tan inverse of, because XC is higher, so XC minus XA divided by RA. Okay, so if I increase my XC, my theta A will increase, so the torque will increase. So short duty capacitors will have higher reactance, so they will produce high starting torque. So the starting torque for short duty capacitor will be high. Okay, so it will produce, short duty capacitors will be high starting torque, but their voltage rating is lower, so I cannot always use it, high starting torque, right? But I cannot always use it for, I cannot always use it. Okay, that is the problem here. So because the voltage rating is lower, that's why sometimes long duty capacitor are used when the like rating of the motor is higher. Higher rated motor, I cannot use short duty capacitors. Okay, so same thing, similar to split phase motor, an electrolytic capacitor is connected in series. The capacitance creates larger phase shift closer to 90, because 90 sin 90 is 1. So that is the main purpose between the two currents, enhancing the rotating magnetic field. The capacitor is of sorry, this will be actually low value. Capacitor will be low value, this will not be high. So here there is a typo, because the reactance will be higher, right? This will be low. So once again the same thing, I will get high starting torque. This will produce high starting torque. Graph behavior will be almost same, but the starting torque will be much higher than the previous. So this was the torque with the resistance split. I will get higher starting torque. Why? Because the angle phase shift has increased, right? So that's why I will get higher starting torque. So this is the high starting torque. Okay, so I will get high starting torque. So that is the case over here. I hope you have understood this point. Produces high starting torque, so electrolytic capacitors are used. So not high value, sorry, low value. Low value. Low value, short period of time. Okay, so cannot use it continuously because there can be possibility of damage, because the capacitance itself is low. So due to that it can get heated up. Okay, I cannot use it continuously. Now there is another one, that is capacitor run. So capacitor run basically means I am using a long duty capacitor CLD, which will be continuously used. Continuously use. Okay, it will be continuously used no matter what. Okay, so yeah, so in capacitor run everything is same, there is nothing difference, just that the this x as xld will be smaller than xc SD, so your phase shift that you will be able to get theta LD will be smaller than theta SD. That's it. So the starting torque will be smaller than the starting torque of the short duty capacitor. That's it. There is no other difference. So same thing graphically also I have shown you that this is the starting torque of the capacitor start motor, and this is the starting torque of the capacitor run motor. So it will be somewhat lower. Okay, and of course, but still it will be higher than the resistance split because that theta angle is much smaller, that is 30 degree. It will be somewhat, here the theta angle will be somewhat like 60 degrees, something like that, right? And here I can get almost 90 degrees. So 90 degrees will give me maximum angle. Okay, so yeah, that is the thing over here in capacitor run. Nothing to explain here. Yeah, that is yeah, single high value. This will be high value capacitor. Okay, I will not have enough space actually here. Okay, so yeah, I hope you have understood this point. So there is another kind, because I want to utilize the good things of both. So I will have a capacitor start, capacitor run induction motor, while I will close this switch for starting and I will open this switch for running, and normal operation I will close the switch. Okay, so I will take use of the both capacitor start and run. So this is how we can use, okay, with capacitor start and run. So it's the same, just that the CS will be used during starting and CR will be used during running. That's it. So a short duty capacitor will be used, which will have low value, not high value, sorry, which will have low value, and a long duty capacitor will be used, which will have higher value, low and high. Okay, so these are the use cases basically. So during startup, CS and CR are connected in parallel, delivering high starting torque. Okay, so yeah, not in parallel actually. So this operation is wrong actually, because only during startup only CR will be used. Okay, so basically we take help of both the characteristics. Both, it has better starting torque and good running torque. So it will be better. So applications we use it where high starting torque is required, like air compressions, and running torque is also required moderately high. Okay, that is the advantage. So basically there is another type of motor, that is shaded pole motor. So what is shaded pole motor? So in shaded pole motor, we actually make few modifications in the poles of the motor. So we punch holes in the pole shoe near the pole face. Okay, not the pole shoe, pole face. Okay, then we add short circuited shaded coil. These are known as shading coil. So we will wound. So this is my like 3D figure of the pole. Okay, and what I will do is I will wound my shaded one. Okay, so if I am wounding a shaded coil, what will happen? So we know the pole faces are generating a sinusoidal flux. So a flux is getting generated, which is a pulsating wave, right? So initially this will be north pole and this will be south pole. Okay, so flux will go from here, but slowly the flux will reduce magnitude. Then slowly the flux direction will change, right? Slowly it will be in this direction. Then again it will increase in this direction. So it will increase. So if it increases, what can I say? So this shaded coil, right? What is happening is slowly the flux here is increasing, then it is reducing. So due to this flux, and according to Lenz's law, a EMF will be induced, that is ESC, and that ESC will produce a flux phi SC such that it opposes the change. Lenz's law is it opposes the change. So if it opposes the change, what does it actually mean? It opposes the change. So here, if flux is increasing in this direction, it will try to reduce the flux. So basically flux will not be uniform anymore. So previously flux was totally uniform. So if I draw without shading, right, without shading, flux will be totally uniform. Like, I hope you will be able to understand it. Here flux will be totally uniform if it is totally, like it is, if no shading is there. Okay, so flux will be totally uniform. But if this, like I write here, flux will be uniform. But if I am providing some shading, so here the flux lines will be higher, here the flux lines will be lower, only a single flux line. Same will happen here. So here the flux lines will be higher and here the flux lines will be lower, only a single flux lines. So indirectly what is happening, the flux lines are passing like this, right? So there is a, what is there, flux lines are not straight anymore. So it's just like something like I am slightly rotating, flux lines are tilted, flux lines are slightly tilted. So if flux lines are slightly tilted, that means I am providing a very small starting torque, providing a very small starting torque. And what is the direction of rotation of the starting torque? So if I am noticing that the direction of rotation is, the flux lines are like this, right? It is going in the clockwise direction, clockwise. So clockwise means from the unshaded portion of the pole to the shaded portion. So direction of the starting torque will be from the unshaded portion to shaded portion. So what I can say is basically this is basically the direction of the rotation of the rotor. So direction of rotation of rotor is same as the starting torque, right? So this sometimes get asked in examination, what is the direction of rotation of a shaded pole motor? So it will be from the unshaded portion of the pole to the shaded portion. Okay, that's it. Many educators will teach you something else, like they will draw some voltage, current, phasor difference. No, this is the concept, this much only you have to understand. So actually what happens in reality, there are two flux. One flux is the main flux, another flux is the shading coil flux, and due to the phase difference between the fluxes there will be a torque developed. Okay, so both ways you can understand, with this or with simple logic, both will work. So a shaded pole induction motor consists of salient poles on the stator with portion of each pole shaded with shading coil. Okay, so the direction of the rotation will be from the shaded portion to the unshaded portion. Everything else I have explained. It will produce very low starting torque, but it will be very simple. I don't need a auxiliary winding, so that's why no centrifugal switch is required. So all those things are eliminated. So if you need very low starting torque, in those kinds of cases your shaded pole motor are ideal, otherwise they are not utilized. Okay, so yeah, I hope you have understood the comparison. You can go through the comparison, you can read it. Okay, now let's come to the condition to get maximum phase displacement. How will I get maximum phase displacement? So to get maximum phase displacement, ultimately what I will do is I have to find out the mean winding current. What is the mean winding current? It is the voltage divided by the impedance of the main winding theta m, right? So it will be equals to V upon Zm minus theta m. Okay, so now what will be the this is the main winding current. What will be the auxiliary winding current? Auxiliary current, winding current will be V angle 0 divided by the auxiliary winding impedance theta m. Okay, and this will be basically V by ZA into minus theta m. So if I want to the condition for 90-degree phase displacement, what will be the condition? Basically the condition will be, remember, if it is capacitive in nature, so sorry, this will be, this theta will be negative, because if it is capacitive the reactance will be negative reactance, right? So basically my theta a plus theta m must be equals to 90 degree. So simply don't remember any formula, just solve circuit and phasor. Don't remember formula, draw the phasor diagram. If they are asking you to get 90-degree phase angle, draw the phasor diagram and then add the angles, that's it, right? So generally what happens is, sorry, this will be theta a. Theta a is actually, don't remember the formula, theta a is actually generally for a capacitor start run motor, it is tan inverse xc minus xa divided by ra, right? So they will know theta m, and theta a, from this they will find out the condition, and from this they will be able to find out the xc, and xc after finding out they will be able to find out the value of c. Okay, because c is equals to 1 by 2 pi fx 1 by 2 pi fx xc, right? So ultimately in the question they will ask what is the value of capacitor for which I will get 90-degree phase displacement between the main winding and the auxiliary winding. Okay, so what you will do, this will be fixed, you will find out theta m, you will find out theta a. Okay, so you will find out theta m and you will write this equation, theta a plus theta m equals to 90. From there you will be able to find out theta a, and theta a is tan inverse xc minus xa. From there you will be able to find out xc, and your c will be equals to 1 by 2 pi xc. That's it, nothing you have to do, that's it. Another thing is condition for maximum starting torque. Condition for maximum starting torque. Okay, okay, condition for maximum starting torque. So now what will happen is same thing, right? You have to find out the maximum starting torque. How? There can be two cases, either your torque is like two fluxes will be given, phi 1 phi 2, flux of the main winding, flux of the auxiliary winding, and sine of angle between them, right, theta. So either you make this 90, or also either they will give current will be current of main winding, current of auxiliary winding, and sine of theta. So for maximum torque, this you cannot change, this will be fixed, right? But you will be able to change the phase angle. So you have to make this 90. For maximum torque you have to maximize this, right? So that is the only case over here. Now what sometimes what happens, your this is fixed, right? Your Z main winding will be fixed, but your auxiliary winding things will be variable. So whatever this part is the variable part. Okay, you will see which one like either you have to do some differentiation or something. You will see which one is varying, and with respect to that, you have to find out the condition for which this value will be maximum. That's it. So to find out the maximum torque developed, you just like generally this is fixed, main winding is fixed. Auxiliary winding, these things will change. So you have to find out the condition for which this will be maximum. So that's the summary basically. I don't want you to remember any formulas because you can directly solve it, right? Without remembering the formulas, you can directly solve it. I don't want you to remember the formula. Directly see the question and directly solve it. Okay. So yeah, I hope it is clear. So I want you to show few questions, and I will come back with the solutions. So this is the first question, second question. Like there are a lot of questions. Then third question, fourth one. I guess this one is the yeah, this one is the last one. Yeah, this one is the last one. So try out this question and I will come back with the solutions. So let's solve this question. A single phase induction motor is provided with a capacitor and a centrifugal switch in series with a auxiliary winding. So it's just like the capacitor start motor. Okay. The switch is expected to operate at a speed of 0.7 ns. What does it mean? So it means the switch will open at when the speed reaches at 0.7 ns. Switch will open, turn off at a speed of 0.7 ns, right? So after that, what will happen? The torque will suddenly reduce because only the main winding will be there to produce the torque. Previously, both the auxiliary windings were there, so it was providing more torque, right? So the normal operation will be something, a graph something like this, right? This we have already seen, right? This will be the graph for normal operation where at starting the torque will be very high. Starting the torque will be very high, and then suddenly here the torque will reduce. Okay, because the switch has closed, switch has opened, right? So then only the main winding torque will be there. Okay, now they're telling me, but due to malfunctioning, the switch fails to operate. The switch does not operate at all. The switch fails to turn off. So it fails to turn off. If it fails to turn off, then they are asking the torque speed characteristics. So if it is failing to turn off, then there should not be any sudden change in torque. So this is automatically gone. This is also gone because if the switch fails to operate, switch is not operating. So there cannot be sudden change in torque because sudden change means the switch either has opened or closed. The torque suddenly changes, right? So these two options are eliminated. What is left? C and D. So we know switch will always be on, right? And if switch is always on, that means the torque at the starting will be due to the auxiliary winding, that is this. This is telling me that the torque will be 0. So this is not possible, and this is possible. This is possible. Okay. So option C will be the correct answer for this question. Option C will be the answer for this question. Okay. Let's now solve the next question. A 220 volt 50 hertz single phase induction motor has the following connection diagram. So these are the connection diagram. 220 volt 50 hertz. Okay. MM axis is the main field flux axis. So if I see, this is the main field flux axis and this is the auxiliary winding field flux axis. The direction of the winding axis indicate the direction of the flux. So these are my direction of the flux. Okay. Parameters of each windings are indicated over here. Now, when the switch S closed, the motor will rotate clockwise, anti-clockwise, do not rotate, or rotates momentarily and comes to halt. So which one is true over here? So before understanding this, right, let's cover a small topic that I forgot to discuss regarding the direction of rotation. Okay. So how can I identify the direction of rotation? So direction of rotation. How will I identify this? So there is a very simple trick, right? So I know, let's assume that my main winding current is IMW into IM peak sine of omega t minus theta MW. Okay. And my IAW is equals to IA peak into sine of omega t, let me write this theta m only, and let me write this theta a. Okay, now one more thing, we know that your flux in the main winding is proportional to current, right? Because flux is proportional to the mmf. So flux is proportional to mmf, right? Imw. Okay, so if I assume my initial current to be in this direction, okay, now what will be the flux value? So let's take a few assumptions. If my Imw is here, okay, and I want to calculate the flux value, so Iaw will be so let us assume this, that this is my voltage, okay, this is my voltage, and my main winding is more lagging. Okay, main winding is here, Imw, and the what do you call, this is my auxiliary winding current. Okay, and my flux is proportional to current. So let us assume a case, that is my theta m is greater than theta. Okay, so yeah, theta m is greater than theta a. Theta m is greater than theta a. So if I assume this case, then let's assume that at omega t equals to theta a. At omega t equals to theta a, what will be this value? Omega t is theta a, so theta a minus theta m. So this is something negative, right? This value is something negative. So your Imw is something negative, right? So your flux also will be something negative. Negative meaning it will be somewhere here, just opposite. This will be my phi Mw at omega t equals to theta a. Now second case I will take, not second case, at omega t, second time instant I will take at omega t equals to theta m. So at omega t equals to theta m, at omega t equals to theta m, what will happen? Omega t equals to theta m, this will be 0, but remember, what is your overall flux? Your overall flux phi resultant is the sum of the main winding flux plus the auxiliary winding flux in the air gap, right? So here actually the auxiliary winding current is 0, because if I put here theta a, it will be 0. So resultant flux is main winding flux only, that is negative. So this is my resultant flux at this instant. At omega t equals to theta m, what will happen? This will be 0. So your main field flux is 0. Okay, and remember your theta m is greater than theta a. That means this is more lagging than theta a. So theta m is this, theta a is this one. So theta a is smaller than theta m. Okay. Now at omega t equals to theta m, Imw is 0. If I put here theta m, this angle will be greater than 0. That means this is positive. So it is Iaw is positive, right? That means your flux Aw is also positive. That means your resultant flux is also positive, because your resultant flux now is only this one, because main field flux is 0. So if I put here, the direction of the flux will be somewhere here, right? So what I am noticing, initially I was here, now the flux went here, so it is clockwise. So if you tend to forget this, you can understand it conceptually like this. Okay, so if your theta m is greater than theta a, then it will be rotating in the clockwise. Basically your auxiliary winding will follow the main winding. Let's take for the second case. Second case, if your theta m is less than theta a, now at omega t equals to theta m, what will happen? At omega t equals to theta a, what will happen? This will be, this is theta a, okay. Theta m is, okay, sorry, theta m is greater than theta a. Okay, yeah. So at omega t equals to theta a, what will happen? This will be theta a minus theta m, and theta a is greater. So now my main winding current will be positive. Now my initial flux will be somewhere here in the same direction, right? Like this, same direction as the main winding current. Okay, and your other current, auxiliary winding current, will be 0. At omega t equals to theta m, what will happen? At omega t equals to theta m, what will happen? At omega t equals to theta m, you will see that your main winding current obviously will be 0, right? Theta m minus theta m is 0. This will be negative, right? Theta m is smaller than theta a, so this will be negative. So this will come out to be, your auxiliary winding current will come out to be negative. That means your flux is somewhere, because your auxiliary current will be more lagging here, so it will be somewhere here, right? Phi resultant. So what am I observing? I am rotating in the anti-clockwise. Okay, so educators will tell you to remember this, but I am explaining you conceptually what is happening. So is this correct? No, right? It is incorrect, because my analysis is wrong, because this time my theta m is smaller than theta a, so I should start my point with theta m. Basically omega t initially will be lower value, pi by 4, then to increase to pi by 2, something like this. So I will start with lower value, right? So omega t lower value, that is theta m is lower. So here theta a was lower, that's why I had started with theta m, sorry, theta a, right? Because theta a was lower, but here theta m is lower. So this will be my starting point. So in starting point, my auxiliary winding is negative, that is here. Then again at omega t equals to theta a, which is the greater value, my main winding current is positive, that means my resultant flux will be here. So actually the direction of rotation will be again clockwise. I will start from here and I will go in this direction, right? Follow in this direction. Okay, so it will be in the clockwise direction. So I hope now it is clear why it will be why this also will be clockwise, this also will be anti-clockwise, this also will be clockwise. When this can change, if this becomes cos, right, then the direction of the rotation can also change. Okay, I hope it is clear. So now let's first of all find out the theta m and theta a. So what is the theta m? The main field winding angle. So tan inverse x, so xm, right? Xm is 0.1 2 pi into f, 2 pi into f, 50 into 0.1 pi divided by r. What is rm? Rm is 0.1. This will be basically, if I calculate this value, this will be 100 into 0.1 will be, this will be 10 inverse 100, right? 10 inverse 100 is almost like 89 point. Theta a will be equals to tan inverse. So now I am calculating the angle of the auxiliary winding. Okay, so this will be 2 pi into 50 into, remember what is your LA, it is 10 by pi, divided by what is the RA is 10, right? So RA is 1, sorry, RA is not 10, RA is 1, so this is 1, so this becomes 10,000. Okay, this is 100, this is 10,000. Okay, so this will be 1000 tan inverse. So it is almost same, right? 89.94. So I am saying theta m is roughly equals to theta a. So there is no angular or no, there is no phase displacement. If there is no phase displacement, then how can torque be generated? Because torque was proportional to sine of theta m mod of theta m minus theta a. Now there is no phase displacement, it is 0, so developed torque also will be simply 0. Okay, developed torque will be simply 0 because there is no phase displacement. So it will not rotate, it will not rotate at all. Okay, so this will be C. C will be the answer. Okay. Now, a 230 volt 50 hertz 4 pole single phase induction motor is rotating in the clockwise direction. Okay, it is rotating in the clockwise direction with speed this. If the rotor resistance at standstill is this much, then the effective rotor resistance in the backward branch of the equivalent circuit will be. Okay, so at standstill, basically they are telling me the rotor resistance is 7.8. Okay, so if you remember the circuit, this was R2 dash divided by 2s standard circuit. I had the leakage reactance, I am not drawing it, and this was the R2 dash divided by 2 into 2 minus s. Okay, so what do I know is that I know that at standstill slip is 1. If slip is 1, basically this becomes simply R2. This becomes simply R2 dash. So you make slip here 1, this will be R2 dash by 2, R2 dash by 2, this will be simply R2 dash. Now what is your rotor resistance? Your rotor resistance R2 dash will be equals to 7.8 ohms. 7.8 ohms. Okay, this will be simply 7.8 ohms. So R2 dash is given to you 7.8 ohms. Now they are asking me what will be the backward branch equivalent like resistance, right? So backward branch equivalent resistance will be this R2 dash divided by 2 into 2 minus s when it is running. It is running at a speed of 1425 rpm. What is the ns? Ns will be equals to 120f by P. Into 50 divided by 4 by 4, right? So this will be 30 into 50. 30 into 50 is 1500 rpm. So it is 1500 rpm. So s is equals to 1500 minus 1425 divided by 1500, right? So 1500 minus 1425 divided by 1500. So slip is 0.05. Okay, so your slip is R2 dash. R2 dash is 7.8 divided by 2 into 2 minus s. 2 minus s is 2 minus 0.05. Okay, so this will be equals to minus plus 2 divide into 2 into 7.8. so your equivalent resistance comes out to 2 ohm. Okay, so your backward resistance will be 2 ohms, that is present in option A. Like these kind of simple questions come like this. These are very old questions. Recently I don't think they will ask much questions, okay, in from this topic, but they can ask if they want to. So yeah, this is one of the last question, I guess. This is the last one, not one of the, this is the last question only. Okay, so here the following information is given: 230 volt 50 hertz capacitor start, single phase induction motor under standstill condition is given, right? So when only main winding is energized, it is 100 volt 2 ampere 40 watt power it is consuming. That means at standstill condition, the impedance of the main winding will be what? 100 volt divided by 2, that is 50 ohms is the impedance. Now power, they are telling me it is consuming this much amount of power. Can I find out the resistance of the winding? So if I'm applying here 100 volt, it is telling me that the impedance will be impedance will be 50 ohms. And what about the resistance? It is consuming 40 watts of power. So 40 watts of power basically means it is I square R, I square into Rm. So it will be I square into Rm. So it will be 2 square into Rm. Rm is, I don't know, I have to find out. And power loss is 40, right? So this will be Rm equals to 10 ohms. Okay, Rm I got 10 ohms. Can I find out Xm? Yeah, Xm is very easy, right? It will be simply Zm whole square minus Rm whole square whole under root. So actually Xm is pretty high. Okay, I will calculate Xm. So 50 whole square minus 10 whole square under root. So this will be this value will be 48.99 ohms. Okay, what about Rm? What will happen to Rm? So Rm, sorry, Rm I already know. So this is my Rm and Xm. So what is my theta m basically? Theta m is, actually I could have easily found out theta m without all this, right? I could have easily found out theta m, but okay, it's fine. So theta m will be basically tan inverse Xm by Rm. Okay, there is another way to find out theta m that I will obviously calculate. So theta m is tan inverse Xm by Rm, that is this 48.1 divided by 10 tan inverse. So theta m comes out to be 78.46. Now what is the easier way to find out your theta m? So I know that cos theta will be what? P by S. Okay, don't ask me all this. All this have been taught in complex power chapter. So from here I can easily find out my theta m. Theta m will be equals to cos inverse PM. PM active power they have given me is 40 watts. What is the apparent power? It is voltage into current, that is 200. From this also you can easily find out what is your theta m, right? 40 upon 200 cos inverse, again same value, you will get exact same value. So you don't need to even need to find out the value of RMXM, all those things, right? Without finding out the value, you can totally find it. Okay, I mean you can totally find the angle. Now let's discuss about the auxiliary winding. So auxiliary winding, again remember, winding, it's a winding, right? So it will be inductive, but I am adding a capacitance. So they are asking me what is the value of capacitance. So it is a winding, so there is some reactance in that. Okay, keep this in mind, there is some reactance. So in case of auxiliary winding, what they are telling me is calculate the value of the capacitance required to achieve maximum starting torque. How can I achieve maximum starting torque? That is what they are asking me. Okay, so I need maximum starting torque. How will I get maximum starting torque? So this is my voltage here, and I need maximum starting torque. Maximum starting torque basically means that the angle here should be the addition of these two angles will be 90 degrees. That will provide me the maximum starting torque. So one thing you have to keep in mind, that this is my auxiliary winding, right? Ra, like auxiliary winding of course will have some of its own inductance, and I will add a capacitance. So I have to find out the condition for maximum, this angle to be maximum, right? So what is my torque proportional to this? I derived, like I forgot to derive it here. I told you that you have to maximize this thing, right? I told you that condition of maximum, you have to maximize this thing, right? How will you maximize? So this is fixed. Main winding is fixed because ZMW is fixed, but this is varying actually because your XC is varying, right? Your XC is varying, so your reactance is varying, hence overall impedance is varying, hence the current also will vary. So what is your IAW? IAW is equals to simply your V upon ZA, right? That is what your IAW is. Now your ZA itself is varying. What is constant? So I can write my RA is constant. RA is ZA into cos theta A, correct? RA is ZA into cos theta A. So this is what? Remember, this theta is the angle between the auxiliary and the main winding. So auxiliary winding is somewhere here. This is theta A. Main winding is somewhere here. That is theta M. Okay, so auxiliary and main winding, that is theta A plus theta M. Okay, so this theta is theta A plus theta M, right? So I can replace this ZA here. So basically I can say my torque is proportional. IMW is fixed, so I can write this some constant K. IAW will be V by ZA. Again, V is fixed, right? So K by ZA is basically RA divided by cos theta, right? So this will be RA divided by cos theta. Remember, everything else is fixed, right? This ZA is fixed. So ZA is not fixed. RA is fixed. Remember, so RA is fixed. This also will be a constant only. Okay. So basically, what I am telling you, that your torque is proportional to IMW, which is fixed value, V upon ZA. ZA is RA upon cos theta A into sine of theta A plus theta M. Now remember, okay, not this. Give me 1 second. Remember that your IMW, V, RA. RA is fixed. Winding resistance in the auxiliary winding is fixed. I'm not changing it. All these are fixed. So I can directly write that my torque is equal to some constant K, KT or K dash into cos theta A sine theta A plus theta M, right? So can I break this now? I can simply break this, right? So if I multiply and divide by 2, what will happen? So two terms will come out. It is 2 cos A, 2 sin A cos B, right? 2 sin A cos B. What is the derivation basically? So 2 sin A cos B. So it will be sin A plus B. So it is sin. So 2 sin A cos B will be sin A plus B plus sin A minus B. Okay, sin A plus B plus sin A minus B. Okay, so sin A cos B plus cos A sin B and plus sin A cos B. So those two things will be added, minus cos A sin B, that will be cancelled. Okay, so this will be here sin A plus B. So sin 2 theta A plus theta M plus your sin A minus B. So A is this minus B, this will be theta M only. Okay, and again this is again a constant, right? This 2, all these things are constant, correct? So this will be K dash divided by 2, which I don't really care. It is just a constant. Torque is equals to this value. Okay, now I have to maximize this. Remember, this is fixed. Theta M is fixed, right? So this is fixed, right? So this has to be maximum because this is only the variable part. So this has to be equals to what, 90. Then only this will be maximum. In whatever is inside sine, that must be 90, then it will be maximum. So basically I can say that your auxiliary winding angle will be equals to, sorry, 2 theta a plus theta m will be equals to 90 for getting the maximum torque at starting. For getting the maximum torque at starting, this should be the value. That means your theta a will come out to be 90 minus theta m divided by 2. Now if you want to remember this, good, right? It will be good actually if you can remember it. If you want to derive in the examination hall, that also you can do. Okay, so why it is not, like, why is the auxiliary winding plus theta m not equals to 90? Because remember, your current is reducing, because your torque is dependent both on the current and the angle. If it was only dependent on the angle, then I would have maximized this value, theta should be equals to 90. But as it is dependent on the current as well, and if I am increasing xc or reducing xc, the current is changing, then I have to write this in terms of a single variable, right? Single variable that is changing, that is theta a. Okay, now I hope it is clear. So now we will solve this question. So condition for maximum torque will be, for the first part, it will be theta a will be equals to 90 minus theta m divided by 2. Okay, 90 minus theta m divided by 2. Okay, so theta m I already know, so I will be able to find out my theta a. So what will be theta a? Theta a will be 90 minus 78.46 divided by 2. So this will be equals to 90 minus 78.46 divided by 2. So this value is equals to 5.77 degree. Okay, so now this is theta a, and what is theta a? Actually theta a is tan inverse xc minus xm divided by ra, right? So for that I have to actually find out all the values. So yeah, I have to rigorously solve this. So okay, okay, what is so what is za? Za will be the voltage by current. Voltage is 80, current is 1, so za will come out to be 80 divided by 1, that is 80 ohms. Okay, and what is my uh, current basically? Sorry, what is my ra? Ra will be basically this I a square into ra is the power that it is consuming, that is 50 watts. So it is 50, and ia is 1, so ra will be simply 50 ohms. So what will be your xma or xa, right? Xa will be 80 square minus 50 square whole under root, so it is 62.45 ohms. Okay, 62.45 ohms. So that is what my xa is equals to. Now I got my ra, I got my xa, I just need to find out xc, right? I know my theta a, so xc will be equals to tan of theta a. So tan of this, right? What is that? Theta a? Theta is 5.77. So 5.77 tan of this is 0.1, right, into ra. Ra is 50 actually, and plus xm is 62.45. So into 50 plus 62.45, so it is 67.5 5 ohms. Okay, so X is 67.5 ohms. So this is what my XC is equals to. So yeah, now right now, what is the capacitance? Capacitance will be 1 by j omega c. 1 by omega c will be equals to Xc. So your C will be 1 by omega c, that is 2 pi into 50 into Xc, that is 67.5. so this will be equals to into 2 into pi into 50 this. So this is actually 47 microfarad. Okay, so the first one answer is 47 microfarad. So this much amount of capacitance that I have to connect to get maximum starting torque. Okay, now if I am next, what they are asking actually to get the maximum phase displacement. Determine the value of the starting capacitance that ensures the main winding and the auxiliary winding currents are quadrature. So quadrature basically means the angle theta A plus theta M will be equals to 90. That's it, right? Because theta A is here, theta M is here. This angle should be simply 90. That's it. This angle should be simply 90. Okay. So that is the case over here. So I know what is my theta m. Theta m is this value, right? Theta m already we have computed 78.46. So 78.46. So my theta a will be equals to 90 minus 78.46. So it is 11.54 degrees. Okay, this is what my theta is equal to. Okay, so now this I will replace it over here. Same thing I will do. I will replace it over here. So my theta a is this. So this is equals to my tan inverse Xc minus Xa divided by Ra, right? So tan of this into Ra, that is 50, plus Xa is 62.45. So it comes out your Xc comes out to be 72.66 ohms. Okay, 72.66 ohms. So yeah, that is the case over here. So this is my Xc, right? This is my Xc. Yeah, so what is my C basically? So I know Xc is equals to 1 by omega c. So your C will be 1 by 2 pi into 50 into 72.66. So into 2 into pi into 50. So it comes out to be 43.8 microfarad. Okay, so if I want the angle to be 90-degree quadrature both the currents, that means like this is my auxiliary winding current and this is my main winding current, right? If I want them both to be quadrature to each other, then I have to provide a capacitance of this much value. So depending on what kind of operation you require, you will provide that value of capacitance. Okay, so now let's discuss about the last topic, that is universal motors. So universal motors is nothing but a DC series motor. That's it. So a DC series motor can support to operate under AC supply. Why? Because the torque is proportional to Ia into phi F, right? And I know in case of a DC series motor, your current, armature current and your field current are same. So basically your torque is directly proportional to Ia square, and whenever there is a square term involved, so I know current is sinusoidal. If current is sinusoidal, for a certain second, for a certain period it will be positive, for the other period it will be negative. So average of sinusoidal is 0. But as it is proportional to a square, so sinusoidal graph is this, right? So average of this is 0. But as it is proportional, as my torque is proportional to square, so the graph will be somewhat like this. This will be the graph. Is the average here 0? Average is not 0. So the average torque is not 0. There will be some unidirectional torque developed. So that's why we can use our DC series motor as universal motor, because the average torque is not 0 even if I am applying a sinusoidal voltage. That's it. Okay, no need to use any brains, this much only you have to understand. Okay, so yeah, that's it basically. So you can go through, read through this, but that is the main thing. So few practical considerations we have to understand, that there will be eddy current losses because now frequency is involved, right? So if F is involved, there will be eddy current losses. So for that we need to laminate the core. So we have to do few mechanical changes, but ultimate concept is this one only. Okay, yeah, and compensating windings will counteract the armature reaction under AC. Okay, because there will be armature reaction in the armature current due to the AC current, that will be compensated by the compensating windings. Okay, so yeah, that's it basically. That's it for this lecture, and that's it for machines. And if you have come till then you are actually the one of the very few people who might be watching this video. If you are, you can obviously text me. If you have watched till the end of machines, that's like big deal. And trust me, whatever I have taught you for machines, that is the maximum that can be taught for gate examination. Okay, you can go and see any paid course, this level of content in this much deep manner and with this systematic manner, no one will teach you. You can compare, you can see any other videos like you have watched till then, then you will know, right? So yeah, I hope you have enjoyed this whole series. If you did, make sure to like share with in your college group if it's possible. And yeah, that's it basically. If you found it enjoyable, you can text me in Telegram. I will be happy to reply. And yeah, that's it basically. I will see you in the some next video. Until then, happy learning.